Assalamualaikum. This topic is about equilibrium analysis in economics, and this topic is actually a static analysis or a static comparative analysis in which we have very simple analysis of equilibrium that doesn't take into account too many variables except, for instance, like at most three. All right. So here, or we can also have more than three. However, when we analyze it, it's just like you analyze between these two, and the remainder of the variables are kept constant or ceteris paribus. So that's why it is, one part of the static comparative analysis. But the opposite of static comparative analysis is what we call dynamic analysis. And dynamic analysis is that we see, you know, two or three different types of factors affecting, one variables simultaneously or at the same time. Okay. Now, let's look at equilibrium analysis in economics today. And this is not something new actually. Why? Because in the study of economics, at least at the principal level, you have heard the term equilibrium. For instance, equilibrium in market for a product. Okay, equilibrium at macro level, for instance, between IS and LM, and so on, so forth. So, if you read the textbook, equilibrium analysis here, or equilibrium itself, is actually a constellation of selected interrelated variables, so adjusted to one another that no inherent tendency to change prevails in the model which they constitute. So that means when we have equilibrium, and if the equilibrium is stable, there is no tendency for any of the variables in the subject matter change. Okay. So this is equilibrium. Now, when we talk about equilibrium here, like I said, because we are studying about the comparative and static comparative analysis, so we want to look at the first type of equilibrium. We call it partial equilibrium. Or specifically, we want to study about market equilibrium, but this is partial. And to make it even simpler, we want to look at the linear model. Okay. Now, what's the idea? We want to find a set of values of the endogenous variables. Okay. So this set of values of endogenous variables must satisfy the equilibrium condition of the model. Now remember, we want to look at the market equilibrium, specifically partial. Okay, so we want to employ example of price determination in an isolated market. Let's say one product market only. So we need to construct a model. So let's say we want to look at one product or one commodity. Okay, we only need to choose three variables, and what are there? Okay, so of course we want to look at the price. Okay, and if we talk about market, of course there are demand and supply, so we want to look at the quantity demanded and then quantity supply. So all of these, we want to find what's the value of price, what's the quantity demanded, what's the quantity of supply at the equilibrium level. Okay, and before we can find them, we need to have some assumption, okay, regarding how the market works. Okay, so specifically, the first thing is that we need to know when it comes to equilibrium, that means quantity supply equals to quantity demanded, isn't it? Quantity demanded, yeah. That means quantity supply minus quantity demanded becomes zero because they are equal, isn't it? All right. Now, because we need to have, like I said earlier, price, quantity demanded, and quantity supply, we know that quantity demanded here, based on the economic study, when price increases, quantity demanded decreases, and vice versa. And this is basically law of demand. On the other hand, when we talk about quantity supply, they have positive or direct relationship between price and quantity supply. So here, to be more precise, this is what I mean. Quantity demanded is decreasing linearly with the level of price. On the other hand, quantity supply is increasing linearly with the level of price, such that quantity supply must be positive for all P greater than P prime, for instance. What is P prime? We need to see in the graph after this, yeah? So here, we want to have a model that contains an equilibrium condition, and we must have two behavioral equations. What are those two behavioral equations? Of course, we must have equation for supply and equation for demand. Okay, so these two equations, or specifically behavioral equations, govern supply and demand sides of the market, yeah, respectively. So let's look at them, in terms of model, mathematical model. Equilibrium condition is number one, yeah, quantity demanded equals to quantity supply. And in the expression 2 here, you can see quantity demanded equals to A minus BP, such that coefficient A and coefficient B are positive. And quantity demanded here, as you can see, if we take the first derivative of quantity demanded with respect to price, then you can see minus B, which is negative. Then this one shows you law of demand, isn't it? And how do you know quantity demanded here? I mean, the expression 2 or demand curve here is downsloping because of this sign, isn't it? And how do you know it is linear? I did mention to you we are analyzing linear model. Therefore, in order for you to be so sure about it, take the second derivative of demand function. Then you can see minus b with respect to p here is 0. Okay, then this one shows you that the slope is constant. Okay, so same thing goes to supply. You can check it yourself. But supply here, as you can see, if you take the first derivative, it has positive relationship between price and quantity supply, and we can see the coefficient here. The value of C and D must be positive as well. So here you can see quantity supply is up, increasing linearly with the level of price. So it has positive relationship between price and quantity supply. So these are the components of the model. Now, if you want to put it in the form of graph, let's say this frame of diagram. On the vertical axis, we put quantity demanded and quantity supply. On the horizontal axis, we put price. Yeah, I'm sure you feel a bit different when it comes to mathematics, because when you studied market equilibrium, what you saw in the economic textbook is that quantity is on the horizontal axis and price is on the vertical axis. And what I'm trying to do here is that to draw it following mathematics rather than economics, but they are the same thing anyway, okay, in terms of answer and analysis. All right, so I won't show you how to get downsloping demand curve and also upsloping supply curve. All of these are basic of drawing graph. Just put the graph straightforward here in this frame of diagram. So if we have demand curve, then it is a linear and straight line. So I have this, and the intercept here, if you follow the method of drawing a graph in mathematics, then you know that this one is A. Try to figure out how to get this value. So this is quantity demanded equals to A minus B, P, isn't it? Now, let me extend the vertical axis here. And here, we want to draw the supply curve, which is upsloping, and it looks like this, for instance. So this is quantity supply equals to minus C plus dP, and the vertical intercept here is basically minus C, and the value of P is here, okay, when P is 0, not P is 0, but the value of P is here, call it P prime, for instance, when quantity supply is 0. That's the correct way of interpreting it. All right, based on the graph, when we talk about equilibrium, here we always refer to the condition that we saw earlier. In equilibrium, condition is in expression 1, in which quantity demanded equals to quantity supply. So quantity demanded equals to quantity supply is at the intersection between supply and demand curve, which is here, okay? Then you can get P star here to denote, not P star, no, Q star, that's the correct one. Q star to denote equilibrium quantity, okay, in which we can have quantity demanded equals to quantity supply in it, okay, and also equilibrium price is here, I call it P star. So we can have here Q star and P star. That's in the form of graph. However, at a higher level, not all the time you need to draw a graph, especially when the equation is a bit more complicated. Then the mathematical operation or arithmetic operation needs to be used in this case. So to do this, we need to have methods of doing or searching for equilibrium quantity demanded and supply as well as price. So one way of doing it is by finding out through elimination of variables. Okay, so this is a process of finding the answer by successive elimination of variables and equations through substitution. Okay, we know that we have these three different types of expression. This is equilibrium condition, this is quantity demanded, this is quantity supply. In equilibrium, okay, we know that QD equals to QS, isn't it? So in this case, instead of writing QD equal to QS and blah blah blah, then we use one representative, call it Q star, to denote equilibrium quantity, because here, based on this writing, Q star equals to QS equal to QD. Alright, that means if we try to arithmetically find the solution, okay, by elimination of variables, then we have this condition, okay, then we can rewrite 2 and 3 previously as Q or Q star. Let's say I put Q star here, okay, as Q star. Instead of writing QD in expression 5 here, we change it to Q star. This one also to Q star, so that we standardize the symbol for equilibrium. Okay, now the next thing is that then you solve the 5 and 6 equations here, similarity. So we have A minus BP equals to minus C plus DP. Okay. Now, when you equate them, then the equilibrium price here, I put P star. Okay. So collect all the term with P on one side and all the term without P on the other side. Then when you solve it, you need to show the method. Yeah, I just jumped the method. Then you can have what we call P star equals to A plus C over B plus a D. Okay. Now, of course, I didn't show you what happens in the middle here, but you have to figure it out. Okay, now, once you get P star, this becomes very easy. You can easily substitute P star back into either 5 or 6 to find equilibrium quantity for this market. Okay, so if you substitute it, then you solve it, then you can get Q star here equals to AD minus BC over B plus a D. Now, I won't show you the algebra here because this one is extremely easy. Now, so here we have equilibrium price as this. We also have equilibrium quantity as this. Now, we know that based on the graph, equilibrium price and quantity, both of them have to be positive. Okay. Now let's go back to the answer that we found. P star, A by condition is positive, isn't it? C by condition is positive. B by condition is positive. D by condition is positive. So since A, C, B, and D all are positive, so P star is positive, isn't it? Because of this condition. What about Q star? B and D positive, so there's no problem for the denominator value. We know AD, both of them positive. We know BC, both of them positive. But then we have minus sign here. So you can see clearly Q star can be negative if AD is smaller than BC, isn't it? Then to make sure that this equilibrium, sounds, reliable and can be referred to, then we need to put restriction. What's restriction? Q star has to be positive such that AD greater than BC, isn't it? Then we can have Q star greater than 0 or positive value. Otherwise, it doesn't make sense to have equilibrium in a market in which quantity, equilibrium quantity is negative value. All right. Now, we can say that after solving all of these algebraic functions, which is very easy actually, we can say that the two sets of points on the demand and supply curves as well as their intersection can be rewritten mathematically like the one in expression 7 here. Now, look at the expression 7 here. Demand is actually a set of price and quantity evaluated at this function. And what is this function? Q equals to A minus BP. Okay? And supply is actually a set of combination of price and quantity in which quantity is evaluated at minus C plus D P. Okay? And in equilibrium, these two sets must be equal or intersect each other like this, such that it gives us equilibrium value for price P star and also Q star. Okay? We have seen a very simple example of equilibrium determination using linear model. Okay? Now we want to extend further the analysis, make it a bit more sophisticated by having a nonlinear model. In fact, in reality, not all the things are linear. If it is linear all the time, then the life is so smooth, you don't feel any obstacles and challenges. So here, let's look at the same analysis, partial market equilibrium, but this time we are using the nonlinear model. So we still have isolated model for market, but because it is nonlinear, we opt for the simplest form of nonlinear function, that is quadratic function for demand curve. But the supply remains linear, so that the analysis becomes a bit easier to do. So here, we still have equilibrium condition, which is quantity demanded equals to quantity supply as expressed in expression 8. And then the modification happens in demand curve or demand equation or expression in 9, in which QD equals to 4 minus P squared. This is where nonlinear comes into the picture. And as you can see, expression 10 is a linear one. Quantity supply equals to 4P minus 1. Alright, now here, based on this, if you do mathematically, you can solve expression, and find what is equilibrium P and what is equilibrium Q in it. But then, look here, we know that equilibrium condition is QD equals to QS, isn't it? And we know that QD is actually 4 minus P squared, and QS is actually 4P minus 1, isn't it? Okay. Now, if we rearrange it, then we can get something like this. You try it at home, but then I jump the step. In the middle here, we have some steps. So here, we're going to get P squared plus 4P minus 5, and then equals to 0. All right. Now, here, let's call this expression 11. The issue here is that you can see we are talking about quadratic equation because it equals to 0. Okay. And if you look at expression 11 here, this is a function. Okay. This function is a function of P or depends on P, isn't it? So we have the issue of quadratic equation versus quadratic function. Okay, so if you look at 11 here, it constitutes a quadratic function. Why? Because 11 is a function of P, isn't it? Therefore, we can rewrite 11 here as the following. So, because 11 is a function of p, therefore I can rewrite it fp equals to p squared plus 4p minus 5. And let's say I call this 12. Okay. Now, if you look here, equation 12, it actually specifies a rule of mapping from P to FP, isn't it? So usually FP here, let's say equals to Y. So it's actually a mapping from P to Y, isn't it? And because Y is actually equal to FP, it's actually mapping from P to FP, isn't it? Okay. Now, from here, let's say we want to see what is the value of fp for a given p. So what I want you to do is that try to find a value of fp for any p between these, as long as it is greater than minus 6 but then smaller than 3. Okay, so let's say p is here, fp is here. So let's say fp is minus 6, minus 5, minus 4, minus 3, minus 2, minus 1, 0, 1, and 2. If p is minus 6, okay, we use 12. We are not using 11, yeah? Because if we use 11 equals to 0, then it means you don't talk about other different types of value of p. So if p is minus 6, you substitute p back into 12, then you get fp equals to 7. For minus 5, you get 0. For minus 4, minus 5. Minus 8, minus 9. Minus 8 again. Minus 5, 0, and 7. Okay, so for different value of p's, we can get different value of fp for 12. Now, let's go back to equation 11. Equation 11, it is a function of p, but then it equals to 0, isn't it? So here in 11, we have quadratic equation because of the sign here, equation. And we here only have one variable here, that is p, not y, not fp together with p, isn't it, for 11? I hope you get what I'm talking about. So here we have restricted fp to be equals to 0, isn't it? Okay, in 11 we have restricted that fp equals to 0. That means not all p here that we have calculated here can satisfy 11, isn't it? Okay, there will be only specific p values that can satisfy fp equals to 0 or 11, isn't it? This one is fp also, but we make it specific, equals to 0. And here, do you realize that there are specific values of p that can satisfy 11 or fp equals to 0? And do you realize that these values of p's that can satisfy fp equals to 0 or 11, expression 11 here, must intersect the horizontal axis? How does it look like? So here, we actually need to solve expression 11 here to find the p values such that fp equals to 0. Okay? Because we only want to find p values, so bear in mind that these answers are not in ordered pairs of p and q anymore. It's just p, not p and q. You get what I mean? And do you realize that p values in 11 here are the roots of the quadratic equation of 11 itself? Okay? So, what are the two horizontal intersections in this case, isn't it? So, we need to put it in the form of graph. Let's say this is the frame of graph. we need to put it in the form of graph. So we have FP here, we have P here. All right. You look here, these are the combinations that we found earlier, isn't it? For different types of value of P, then we can get FP. Without graphing, you can see that value of P that leads to FP equals to 0 are 2, okay, minus 5 and then 0, 1 and then 0, isn't it? So if we put in the form of graph, all right, so let's say roughly speaking, minus 5 is here, roughly speaking, yeah? And we have, if you look here, minimum point here for FP is what? Minus 9 minimum point, yeah? Minus 9 FP when P is equals to minus 2. Okay, so let's say minus 2 is here. Then we have here minus 9. This is the minimum point. And P0, okay, then FP is minus 5. That means when P0 here, FP is minus 5 somewhere, let's say here, minus 5. Okay, and FP0, like I said to you, minus 5 and 1. So let's say we have 1 somewhere here. Okay, let's say 1 here. So if you join all this point, then slowly join it to get good drawing. Then you can get something like this, yeah? More or less like this, okay? So here, as you can see, this is a quadratic function. Fp equals to p squared plus 4p minus 5. But Fp will be equals to 0 at this point and at this point when p is equals to minus 5 and p is equals to 1. All right. So graphically, we solve this p using graph quadratic function like this. Then we know that if you can recall back, the Fp equations here, Fp equals to p squared plus 4p minus 5 is actually originated from equilibrium condition that we have earlier in equation 8. Let me rewrite it again here. If you can recall back, Qd equals to Qs. Okay, this is equation 8. And then specifically, Qd is 4 minus p squared. And Qs is actually 4p minus 1. Okay, and then we arrange it in such a way that it leads to this. Okay, that means 4 minus p squared minus 4p minus 1 equals to 0, isn't it? All right, if we want to fulfill equilibrium here. But if we don't set that equals to 0, then Fp can take any value, yeah? But if we set it equals to 0, okay, then Fp equals to 0 only appears when p is equal to 1 and p is equal to minus 5. Okay, now my main point is to show you that in mathematics, if you want to find equilibrium conditions of economic study, for instance, there are many ways to do it. Apart from eliminations of some, variable, like what we did for the linear case previously, another way is to form this, to solve it using these methods. Okay, when you see there's a quadratic form, you can actually solve it using this method, equate it equal to 0, because, the left hand side, if it is equal to the right hand side, when you have left hand side minus right hand side, then it becomes 0, and that 0 is actually FP at certain value of P. Alright, now for the equilibrium conditions in economic study, especially in the market of isolated market in this case, we know that price cannot be negative. So the answer here, we don't choose price equals to -5, but we choose price equals to 1. Okay, for equilibrium price. Now from price equivalent to 1 here, then you substitute it back into QD or QS, then you can find equilibrium quantity. Alright, I hope this is very clear. Alright, so if you are very good in mathematics, then if you stuck with one way to find equilibrium, price and quantity, then you can also use this way or other ways to find it, as long as equilibrium conditions is whole from the beginning. Alright, so this is for a nonlinear example. So here, let me repeat again. If you look here, P values in this case, okay, are actually the roots of the quadratic equations of FP. This FP is actually quadratic equation, yeah? And so P value that we found here, -5, and 0, -2, and -9, 0 and 1 here are, so -5, -2, 1 are the examples of P values that are the root of the quadratic equations here. Alright, but the root that we want to find for the case of equilibrium condition here is the root that leads to the answer of FP equivalent to 0, because if FP equivalent to 0, then we know that quantity demanded equals to quantity supplied. Okay, so let's crack on. If you look at this quadratic equation or expression here, I did mention to you about the root, okay, and in this case, for this expression, which is expression 11, let me recall by expression 11. For expression 11, FP equals to P squared plus 4P minus 5 equals to 0. When it is equal to 0, like I said in the graph, it is here and here, isn't it? What does it mean by FP equals to 0? FP equals to 0 means quantity demanded equals to quantity supply. Why it means quantity demanded equal to quantity supply when FP equals to 0? Because, in order to get FP, the quantity demanded here must be minus quantity supply, then you get 0. Okay, no difference. Yeah, and here, in 11 here, we solve equation 11 using graph, isn't it? Okay, using graph. But now, there's another way also to solve it. In other words, to find what's the equilibrium price. In graph, we have found equilibrium price to be 1, not -5, yeah? Because we rule out any negative value of price, okay? But there is, like I said just now, there is another way to solve it, that is using algebraic method, okay? So we need to use algebraic method here. I'm sure you have seen this formula. I mean this, yeah? Let us see this formula. The quadratic formula, okay? You look at expression 13 here. A times x squared plus bs plus c equals to 0, such that a is not equal to 0. If a equal to 0, then it won't be called quadratic equation, because the whole term here will be equals to 0, isn't it? That it becomes linear expression. Okay, now, here, for expression 13, this is just revision of what you have done in your high school or, middle school. Here we have two roots. Okay, we can find them using the quadratic formula below. Okay, and I'm sure you have seen this quadratic formula. It is minus b plus minus in bracket b squared minus 4ac, and then square root the whole of them, and then divided by 2a. Okay, so this is expression 14. As you can see here, we have minus sign, we have this value. Okay, as long as this value is positive, then we can have different value of x1 x1 star and also x2 star. Why this value has to be positive? Because you see, this to the power of half means square root. you cannot square root any negative value. Okay, this doesn't work. So it has to be positive. So as long as this bit b square minus 4ac is positive, then you can always square root it. Then you can always have different values of x1 star and also x2 star. What happens if b2 minus 4ac equals to 0? Now let me clean the mess here so that we can see clearly what I'm talking about. Alright, so if the one in the circle bracket here equals to 0, square root of 0 is 0 in it. Then the whole thing here becomes minus b over 2a plus or minus 0, isn't it? Then it becomes negative. Alright, so the equilibrium x becomes negative. But what happens if b square minus 4ac is less than 0? You cannot square root it. Indeterminate answer, innit? Alright? So that's why when we use mathematics in this case, yeah, to find equilibrium quantity or whatever kind of economic condition we want to find, make sure you know the intuition, economic intuition behind it, so that you can always rule out any possible answer that doesn't give you any economic intuitions. Now, for instance, like I said just now, you want to find equilibrium price, but here obviously equilibrium price that leads to, FP equals to 0 are 2, minus 5, and also 1. Obviously, there is no such kind of thing so-called minus 5 quid or minus $5 or minus 5 pound sterling of price. Yeah, so we rule out this. All right. Now, the next thing is that let's look back at this formula. Let me clean up the mess first. So if you look at this formula here, do you know how it is derived? Yeah? Do you know how it is derived? I want you to try to derive it. There is a way in the textbook, yeah, talking about the derivation of this formula. Okay? What you need to do is that this one has to be set into equals to 0, otherwise you cannot get it. From here, you rearrange it until you get x equals to what? Okay? Then from there you can derive this formula. So I hope you can try it. That means you have to read the textbook in order to derive it, so that you can have, economic intuition behind it also, and also mathematical intuition behind it. There is another way to do the same exercise here, yeah, for quadratic function of equilibrium in the isolated market. So we are looking at another different types of graphical solution, but here I won't show you in detail. I just want to guide you, and then you should try at home. So again, if we look at the equations, it is really written again here. For the demand, it is Q equals to 4 minus P square, and for the supply, it is Q equals to 4P minus 1. Now, what you need to do here is that, okay, instead of using quadratic equation like what we did in 11th and also 12, we use these two equations, put both of them in the graph. That means in the graph, now you don't eliminate Q, yeah, you have P and Q. So you have Q here or P here. And also, you don't only have one curve, because in the quadratic equation that we have here, we only have one curve, isn't it? But here, because we consider both variables, which are P and Q, then we will see P and Q in the graph. Also, we see two different curves, demand and supply. And using these two different curves, you find Q star and P star simultaneously. Okay, because that is our objective, to find equilibrium price and also quantity. All right. Now, the next thing is, we did see this exercise here. We have the highest degree of polynomial, which is 2, isn't it? So we can always use quadratic formula or, factorization to do this. What if the power of the polynomial functions is even more than 2? So we are talking about higher degree of, polynomial equations. Okay, so here, if you just imagine that if the system of simultaneous equations, if you try to, factorize or whatever, it doesn't reduce to a linear equation like what we did earlier. Let's say it stay the same to cubic or quadratic or quartic instead, then it's very difficult to solve to solve for the roots. Okay, so it's not easy to find the root. Then how to solve this problem and or how to find the solution here? So one way is by factoring the function. Okay, so let's say we have this function here. I'm writing it down. In fact, it is in the lecture slide also. So we have x cubed minus 4x squared minus 9x and plus 36 equal to 0. So we have polynomial equation because we are equating it to 0. And you see the highest degree of polynomial power or exponent here is 3. So we have x cubed 3. Okay, now let's call this equation as expression 16. The question is we want to find the root for x. How many possible roots for x in this case? How many can we find? Okay, so we can do or we can perform the factorization to find the answer. But how to perform it? Because it's not very directly, or easily, found, because it is not a quadratic function. Now, let's look here. We try to group this on the left hand side. This is the left hand side equals to the right hand side. Yeah. Look at the left hand side here. We try to group it accordingly to two different groups, so that after that we try to factorize it using the greatest common factor for each of the group. Yeah. So let me use a different color of pen. Now the first group would be x cubed minus 4x squared. This is what I observe. And the second group would be minus 9x plus 36. Okay. Now if you look at the first group here, if we factorize, okay, 16, then it yields what? We can have x squared because we have common factor here, and then in the bracket x minus 4 in it. And then what about the second group? This is the first group. Okay, this is the second group. In the second group here, we can see the common factor is 9 because 9 times 1, 9. And on this side, 9 times 4, 36, isn't it? So here, we take out 9. Okay, we take out 9 here. Then it becomes, or even we can also have minus 9 instead of 9 so that we can have easier calculation. 9, and then we have x minus 4. Then we can have another different, factorization. Can you see what I mean? Because minus 9x times x, you get minus 9x. Minus 9 times minus 4, you get 36. Is it clear? Now, from here, then you can still factorize it even further. Okay, because we have common factor here. What's the common factor? X minus 4 here and x minus 4 here. So we factorize that we get this. X squared minus 9 bracket times x minus 4 equals to 0. In it. Now, this can be further, can be further factorized. But before we factorize it, we write it this way. X squared minus 3 square in it. And then x minus 4 equals to 0. Do you get what I mean? Right, this is simple factorization that you already learned in the high school. And from here, we can factorize this bit even further. That is x minus 3 times x plus 3, and then times x minus 4 equals to 0. So from here, we can find the root. How many roots can we get? We have 3 different roots because this one is already simple. So the first root here is x minus 3 equals to 0. That is x equal to 3. The second root here can be found by using this arithmetic operation, x plus 3 equal to 0, which is x equals to minus 3. And the third root here can be found from here. So x equal to 4. So we have 3 different roots for expression 16. X equal to 3, x equal to minus 3, and also x equal to 4. All right. Now, you can recheck it again, put all of these, whether you can get, the same expression as 16. All right. Now, here, if you realize, the highest power of polynomial, I call it n, equivalent to 3, isn't it? And then we have 3 different roots. How many possible value of x here? Or x star? Okay, let's put x star here because we want to find equilibrium in it. Okay, so we have x star could be, minus 3, 3, and also 4. Okay, now here, you look at the constant term of this expression, which is 36. Now, the constant term here is 36. If you realize, the constant term of 36 is actually the product of the 3 roots that we already found. How do we know? You have, for instance, here, 36 equals to 3, and then, okay, times 4. Then you can have 12, isn't it? And then times minus 3. Now, wait a minute. Yep. Okay. So, you can see that in absolute term, we can see that it is actually the product of all 3 different roots, isn't it? Okay. So, and if you see here, each root, okay, is actually the divisor of 36. For instance, okay, if we have 3 minus 3 and also 4, isn't it? This thing is in absolute term because I don't count the minus sign. But now the next concept here is that each root, either 3 or minus 3 or 4, can be a divisor of 36, isn't it? Or divisor of the 36. For instance, 36 divided by 3, you can get, an exact integer, which is 12. Minus 3 here is a divisor of 36, in which you can get minus 12, isn't it? 4 here is also a divisor of 36, in which you can get 9. So all of these are divisors of 36. Okay. Therefore, here, if we have this kind of situation for polynomial and we can find it, the root this way, then it means we can generalize it into one kind of theorem. And what is that theorem? So that theorem shows that, we call it theorem number 1. Given the polynomial equations such that x to the power of n plus a n minus 1 times x to the power of n minus 1 plus until a1 times x plus a constant of a naught equals to 0, where all the coefficients are integer, it's not a fraction, yeah? All the coefficients are integers and the coefficient of x to the power of n is unity or 1, okay? If there exist integer roots, okay, then each of them must be a divisor of the constant a naught, okay, a divisor. All right, now, anyway, let's go back to this example. Let me rewrite it again. So we have x cubed minus 4x squared minus 9x plus 36 equal to 0. If we use generalization here, this x cubed is actually xn plus a n minus 1, okay, xn minus 1, isn't it, this one, minus a n minus 2 x n minus 2, isn't it, refers to this, and then plus a naught equals to 0. So a naught is 36, okay, x to the power of n is x cubed, okay, a n minus 1 times x to the power of n minus 1 is actually minus 4x squared, and this one is plus, yeah. Okay, a n minus 2 times x to the power of n minus 2 is actually minus 9x. Is it clear? So this is the generic form of this. Okay, now, if you look at this, okay, a naught here is 36, okay, and if you look here, this one coefficient is 1, isn't it? Okay, coefficient of the highest degree of, polynomial here is 1. Okay, now, So you can find the root using, you know, this theorem, like I said earlier. But what if we have something else here? Let's say I give you this fraction. Okay, let's say we have x cubed plus 3/4 times x squared minus 3/8 times x minus 1/8 equals to 0. Now, not all of the numbers of coefficients here are, you know, integers. Some of them are fractions. So what should you do? Can you apply theorem number 1? In order for you to be so sure that you can still apply theorem number 1, try to change the left-hand side here. This is the left-hand side equals to the right-hand side. Try to change the left-hand side here, make it integers, not fraction like this. It is possible to change that because we have equal sign equal to 0. So whatever you multiply on the left-hand side here will be always equal to the right-hand side, because whatever number you multiply here and also multiply on the right-hand side, it is always equals to 0. So in this case, what I can do is that if I try to change it, then I can have 8 over 8 x cubed, isn't it, plus 6 over 8 x squared minus 3 over 8, 3/8 x minus 1 over 8 equals to 0, isn't it? So if I simplify it further, what do I have? Then I can have, you know, bring all of the value on the denominator here because they are the same. Bring it to the right, okay? Then you don't have it. Then we can rewrite it, you know, in general. Let me write it here so that I have, you know, because I don't have enough space. So here, I simplify it further, then I can have this 8x cubed plus 6x squared minus 3x minus 1 equals to 0. Okay. Once you are done with this, change it from fraction to integers, then you check whether you can use theorem number 1 or not. Now, theorem number 1 says what? You must have a naught. What is a naught here? Is equivalent to 1. And then you must have the coefficient of xn. Xn is this, isn't it? Because the highest polynomial is 3. So this is xn. And the coefficient is this. Okay. So coefficient of x to the power of n is 8. But if you look at theorem number 1, in order for you to use, you know, this method that I've explained to you earlier, okay, and also to find integer roots using theorem number 1, okay, the coefficient of x to the power of n has to be unity or 1. What's the coefficient of x to the power of n in this case? It is 8. It's not unity. Then, in order for you to find roots, it's impossible to find it using theorem number 1. Okay, it's impossible to find it using theorem number 1. Then we have to resort to another different types of theorem. Okay, that we need to find another theorem. Let's call it theorem number 2. And that means we need to resort to a more general theorem, because this theorem is not applicable to all different sets of, you know, polynomial equations. So theorem number 2 says what? Now, theorem number 2 says, given a polynomial equation with integer coefficients, yeah, whatever value of integer coefficient, as long as, you know, this one here is not 1, this is the constant, yeah. So this is a more general theorem. If there exists a rational root of r over s, where r and s are integers without a common divisor, okay, except unity, then r is a divisor of a naught and s is a divisor of a n. So what does it mean here, class? In theorem number 1, you can see that the divisor that I told you for this first example could be 3 minus 3 and 4. Okay, and could be 1 as well actually, because 1 times 1, 1, isn't it? Sorry, 1 times 36, you can also get 36, isn't it? Now, anyway, let's go back to theorem number 2 here. In this example just now, this one, when we change it to, you know, integer, you don't find any common divisor for this, because the constant a naught is 1, but the coefficient of xn is 8. The only common divisor is 1. Okay? So in this case, what we need to do is that If there exists a rational root r over s, where r and s are integers without a common divisor, except unity, except 1, then r is a divisor of a naught and s is a divisor of a n. That means if you want to find the root for this kind of polynomial equations in which you cannot find, using theorem 1, then you need to find a divisor for a naught here, a constant here, which we call r. You also need to find a divisor for a n here, which we call s, and then you need to find the ratio between these two divisors. And then if the ratio works well to find 0 here, then that's the root basically. Okay, that's the root. Now let's try this theorem number 2 using expression 18. So we have 18 here, 2 times x to the power of 4 plus 5 times x cubed minus 11 x squared minus 20x plus 12 equals to 0. So this is polynomial equation because you have equation here. All right. So can we try solving this 18 using theorem number 2? And if we use theorem number 2 here, we know that we need to find a naught. We know that we need to find coefficient for, x to the power of n. Now, a naught is what? A naught is positive 12. What is the coefficient for x to the power of n? X to the power of n is this because the highest power is 4 here. 3 can't be, 2 can't be. So it has to be 4 because the highest power is 4. So x to the power of n is this. So what's the coefficient? Coefficient is 2. Okay, the coefficient is 2. Obviously, from this, we cannot use theorem number 1. You have to find out why we can't use theorem number 1. So we need to try theorem number 2, whether it works or not. Okay, now, the next thing that we need to do is that, based on theorem number 2, we need to find r, we need to find s. Okay, remember, r is a divisor for a naught, s is the divisor for, a n. Okay, and as you can see here, we cannot resort to theorem number 1 before I forget, because the coefficient for x to the power of n is not unity, it is 2, it's not 1. Okay, let's crack on. So here, what about divisor for r? Remember, divisor for r is, r is actually the divisor for a naught. 12, okay? 12, the divisor could be, 1, isn't it? Because 12 divided by 1, you get 12 integer. What else you can have? Could be 2, isn't it? 12 divided by 2, 6, isn't it? Okay, 3, 4, isn't it? Okay, this one is simple. 6, isn't it? I did mention to you just now. And then what else? We can also have minus 1, isn't it? Okay, you get me? Because 12 divided by minus 1 equals to minus 12. Alright? And then we can also have minus 2. We can also have minus 3. We can also have minus 4. We can also have minus 6, isn't it? Not to forget, remember, 12, divided by 1 is 12, isn't it? So another one is 12. Another one is minus 12, isn't it? Okay, so that's the divisor for n naught, which is r. Now what about s? S again is a divisor for, coefficient of for xn. So what is s? The possible value for s, look here, the coefficient is 2. The possible value for x is actually, or an, is actually 1 or 2, minus 1, minus 2, isn't it? Alright? So because 2 divided by 1, 2. 2 divided by 2, 1. 2 divided by minus 1, minus 2. 2 divided by minus 2, minus 1, isn't it? Okay, so we have listed down all of the divisors for a naught and also coefficient for x to the power of n. Now, before I forget, the coefficient for x to the power of n can also be rewritten as a n. Okay. Now, the next thing that we need to find, if we go back to this, is that, theorem number 2, yeah, we need to find rational roots. That root is a rational because it is in the form of ratio. Ratio of what? R over S, such that R and S are integers without a common divisor except unity. Okay. Well, then R is a divisor of A naught and S is a divisor of A n. Alright. Now, here, we need to find the possible R over S. So, we need to list down all possible R over S from R that we found here and S that we found here. So, you can have, for instance, the first one, 1 divided by 1, isn't it? Let me use red pen. 1 divided by 1, isn't it? So, here, 1 divided by 1 becomes 1. The second one is 1 divided by minus 1. So on and so forth. So if I were to list down all of them, then I can get 1 minus 1, 1 half, minus 1 half. Okay. And then what else? Of course, 2. Okay. This is very easy actually. Alright. And what else? Because 2, and here, 2 divided by 1, you get 2. Okay. And then minus 2, isn't it? And then you can have 3, you can have minus 3, and then you can have 3 over 2, isn't it? 3 divided by 2 here, for instance. Or you can also have minus 3 over 2, 4, minus 4, many actually, as long as it is in the list. And then you can have 6, minus 6, and then 12, minus 12. Okay, I hope I don't miss anything here. So all of these possible R over S are all possible roots for 18. But can we say that all of these are the possible roots and the possible answer for, for roots of 18? We are not so sure until we try all of them, put them back into 18 and, calculate whether it's equal to 0 or not. Okay, that's the thing that we need to do. Okay, how do we do it? Now, let me show you one by one. Let's say, let me erase this because it's very messy. Okay. Let's say we pick R over S equivalent to 1, the first one. What should we do so that we can be so sure R over S equal to 1 is a root or not? Is the answer for 18 or not? So what we need to do, we take R over S equivalent to 1. You put it back into this equation and then check whether the left-hand side here, the answer is equal to the right-hand side or not. And the right-hand side here is 0, isn't it? So check whether the left-hand side here is equal to 0 or not. So when you put it back, then it becomes what? 2 times 1 to the power of 4 plus 5 times 1 to the power of 3 or 1 cube minus 11 times 1 square minus 21 plus times 1 plus 12. Okay, when you calculate it, then you found what? It's actually, okay, equivalent to 12. So 12, and then the question is it equivalent to 0 on the right hand side here? No, it's not equivalent to 0. Then this rule out that 1 can be the root of 18. Next, try minus 1. Do the same thing. Next, try 1 half. Do the same thing until the last one here. Then you can see, all right roots for 18. Now, for 18 here, what are the right roots? When you try to do it one by one, like I said just now, okay, what you get is this. Let me erase because actually I don't have enough space to show you, but the final answer should be this. So R over S that can be, that can be possible roots are basically 1 half, 2 minus 2 and minus 3. So these are all possible roots. So after you found the root, what should you do? You write the factorization answer. So how do you write it? For 1/2, look here, this is how you do it. X minus 1/2 multiply by x minus 2, and then multiply by this is done, x plus 2. You see, this one is minus 2, then it becomes plus. And then multiply by x plus 3 equals to 0. That's how you find the final line of the answer. So you have found the root, that's the answer, yeah? Okay, now, actually this can be rewritten as 2x minus 1, okay, times x minus 2, x plus 2, x plus 3 equals to 0. How do we get this from this? This is very simple maths. You multiply it by, 2 over 2, then the denominator, you can bring it to the right hand side, becomes 0. Isn't it simple? Okay, this is simple maths actually. All right. Okay, so here, this is how you do it. But if you look at this, we can be so sure that, this kind of equation can be solved using theorem number 2. Okay, theorem number 2. Clearly, in this example, we found that when r over s is 1, it's not the root for expression 18, isn't it? Now, the next thing is, what if, okay, the value of the root is x equal to 1? All right, let's say x equal to 1 instead. What would happen here? So, if x equal to 1 is the root for some polynomial equation, let's say this is the answer. But of course, in 18, it's not the answer, isn't it? Because we ruled it out in the first place. But let's say in any polynomial equations, x equal to 1 is the root. Okay, so here, what does it mean is that we can see that all x in the value here, okay, equals to 1. In other words, let me write it somewhere here. Okay, so that means if x equal to 1, so xn equal to xn minus 1 equals to until x equal to 1. Yeah. Now, then the polynomial here would reduce to a simple form like this, which is an plus an minus 1 plus until the last one a0, isn't it? Equal to 0, isn't it? So here, why it becomes an plus an minus 1? Where is the x? Because x here is 1, x here also 1, and the rest of the x here also 1. This we don't have x because this is a coefficient, a constant only without x. Okay, so here, then it reduces to this value. Then we can come up with this kind of theorem that we need to take into consideration. This is theorem number 3. So let's say we have polynomial equations like this, but then, okay, if all a here constant value add up, then it equals to 1, isn't it? Because x equal to 1 is the root of equation. So that means whatever value in a here, you add with this and add whatever value of a in the remainder here, all of the sum of a here add up to 0, then it means the value of the root is 1. Okay, it's the root of equation. So that is theorem number 3. Now, we are done with the factorization for solution of certain polynomial equations if we want to find equilibrium or whatever. So please try exercises from textbook and also from the internet on this. Okay, so here, what you have seen from the explanation in the video is equilibrium in one isolated market. When we talk about equilibrium for static model here, it's not only about the market, it can also be about some other things. Yeah, equilibrium, let's say, in the between saving and investment, equilibrium between money market and also product market and whatnot. Okay, but what I've shown you here, basically from the example of textbooks, are just one example. So please find some other examples from the internet when we talk about equilibrium analysis using mathematics. All right, now we move to general market equilibrium. So what we have done previously are all partial market equilibrium or all partial equilibrium. So if we talk about general equilibrium, what does it mean by general equilibrium? So we have seen the partial market equilibrium. What if, because we want to be more realistic here, what if we have more than one commodity or product? Okay, so in the case of more than one commodity or product, then we call the analysis as general market equilibrium. So let's say we have, excess demand or excess supply in the market. Therefore, we need to show it in the form of mathematical expression. So let's say here, for each commodity we call it I. Okay, so for every commodity I, there is a market for each of them. Okay, so the total commodity I's, you sum all of them, then it consists of total N commodity. Then excess of demand is denoted as EI. Okay, EI refers to the excess demand for commodity I. Now I can be commodity number 1, commodity number 2, commodity number 3 until commodity number N. Alright, so the formal way of writing the expression of excess demand for commodity I, let's say commodity I refers to apple, or I refers to commodity number 1. Okay, it's written as expression 19. In particular, EI is equivalent to QDI minus QSI. Q refers to quantity of output, and in equilibrium, we expect this excess to be zero because quantity demanded equals to quantity supply. That's the condition of equilibrium, so that's why we have a zero here. So as you can see, because we are talking about general market equilibrium, we include several commodities in the market. So here, let's say we look at the simplest case of several commodity, that is two commodity market model. So we use general equilibrium analysis, and we use generic form to analyze it first. Then later you can see numerical example after that. All right. Now for two commodity market model, for simplicity, we adopt linear demand and supply functions for both commodities. So we have two commodities, commodity 1 and commodity 2, and both demand and supplies are linear, And so in parametric terms, now what does it mean by parametric? I hope you can find it. You can try to Google search it and see the examples, and especially the meaning and that example. So in the parametric terms, we have two commodities, so it can be written as expression 21. We have two markets. The first market characteristic is shown by this. Okay, this is for product 1. Okay, the second market here is shown by the last three expression. This is product 2. So you can see the first one here is the equilibrium condition in which excess demand is equivalent to 0 because QD minus QS for commodity 1 is 0. And then this one is actually quantity demanded for commodity 1. And the third one here is quantity supply for commodity 1 in market commodity 1. And if you look at the second one here, the same thing, but now it's for commodity 2. Okay, so this is demand, this is the supply, this is the excess demand equals to 0 at the equilibrium position. Again, let's look at market for commodity 1 here. If you see coefficient A and B, this one, all of this, coefficient for demand and supply function for the first commodity respectively, and hence if you see mi and beta here, these are the coefficients for demand and supply for the second commodity respectively. Okay, so is it possible for us to solve and to find equilibrium price and quantities here? Logically speaking, yes, because you have how many variables? P1, P2, okay, and also Q1, Q2 that you need to find, and you have how many equations? 1, 2, 3, 4. This one is just condition so that they can be solved. Okay, so how to solve it? You need to use, there are many ways actually, but the simplest one is using elimination of variable methods. So in this case, elimination means, what does it mean here? You have, let's look at market number 1 here. For market number 1, in equilibrium position, quantity demanded must be equal to quantity supply. So you equate these two to get this, yeah? So here, that means, if I write it properly, let me erase here so that I can have some space. Okay, so it means if we follow this condition, we need to do this minus this, isn't it? So A naught plus A1 P1 plus A2 P2 minus, okay, B naught minus B1 P1 minus B2 P2. Okay, so minus B2 P2 equals to 0. Okay. Also, in the second market here for commodity, the second commodity, you do the same because you want to have no excess demand. That means you are in the equilibrium position for commodity 2. And it means me naught plus me 1 P1 plus me 2 P2 minus beta naught minus beta 1 P1 minus beta 2 P2 equals 0. Alright? Now, if you see here, what happens is that, okay, we have this because we have, Q D1 minus Q S1 equals to 0, isn't it? That's why we have this. Okay, we have this because of this equilibrium position. Now, what can you do next? Because you don't leave it just like that. You need to solve for P1, P2. You can see clearly by the process of elimination of variable methods, what is left is just P1 and P2, the prices for commodity 1 and commodity 2 respectively. We have eliminated Q1 and Q2. Okay, we eliminate it so that we can solve P1, P2. Now we have two equations and two unknown. Two equation is the first one here, the second one is here, and two unknown are P1 and P2. Now what do you need to do is to solve it. But before you solve it, do you realize if I show you using different pen color, let's say I use red. Do you realize that you can, if you see the first expression here, this one and this one has the same common factor, that is P1, isn't it? Similarly, if I use a yellow pen color, let's see this, okay? You can see this and this have the same common factor, that is P2, isn't it? So what can we do? We can actually factorize, okay, to simplify the equation. So if we factorize it, let me erase some spaces so that I can show you the factorization. So if we factorize it, it becomes this. So I factorize it here. I don't write the sentences, but when it comes to your work, you have to write sentences here because I'm teaching, so I omit some sentences. But when it comes to you answering some question, because this is not just maths, this is you must have some explanation so that what are you doing? Whatever you do here being explained thoroughly using economic intuitions and whatnot. Now, here when we simplify it, it becomes what? A naught minus B naught, isn't it? That's the first one. And then A1 minus B1 in bracket P1 plus A2 minus B2 in bracket P2 equals 0, isn't it? So we simplify it. Same thing as this. Okay, if we simplify it, then we have factorize, yeah? Me naught minus beta naught plus me 1 minus beta 1 P1 plus me 2 minus beta 2 P2 equal 0. Okay, then after you simplify, it becomes easier for us to do, to find the answer. So if we write it neatly, this is what I mean just now. You have seen this just now, you have seen this. Okay, so what we found here is that the model that we saw earlier has been reduced to two equations and two variables. Like I said just now, we have two equations and two unknown. Those unknown are P1 and P2. Okay? All right, this is what I meant just now. So what equation in 22 here is trying to show us? Okay, so what does it mean when both of them are equal to 0? Okay, and here if you look at how many parameters or coefficient, okay, and how many unknown, you already know there are two unknown, P1, P2, but how many parameters? If you count it, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. You have 12 parameters there. But we want to solve for P1 and P2. Is it possible? Yes, of course it's possible, because this is very simple, because you have two equations and two unknown. I won't show you in detail here, but you need to go through all of them in detail. But if you do it at home, then finally you'll get this. Okay, you'll get something like this. But before you get something like this, you see the parameters here is a lot. It's about 12 parameters. So what should we do? In mathematics, you can leave it just like that, but it's very annoying writing this, isn't it? So why don't we make some summary here? So make the writing simpler. So here, let's say we call it C1. We define C1 equivalent to, or CI. I refers to commodity. We have commodity, 1, 2, not commodity, the coefficient, yeah, sorry. It's not commodity, the coefficient. 0, 1, 2, because 0 for coefficient without, variable attached. Okay? So same thing for gamma equals to gamma I equals to alpha I minus beta I. Okay? So if that is the case, then we can have this. You look here. For the first one here, then this one becomes, C naught, isn't it? Plus C1 P1 plus C2 P2, such that CI equals to what? AI minus BI, isn't it? And I is actually 0, 1, or 2, isn't it? Okay, what about this? Okay, now this one is gamma naught plus gamma 1 P1 plus gamma 2 P2 equals to 0. Okay, can you see here? It becomes simpler to write, so you don't have to write A naught minus B naught, blah, 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 blah. It's very annoying. It needs a lot of space to write this. So here, after that, you can solve it easily, because you don't have to have a lot of mathematical notations. Okay, so when you solve it, then you get the equilibrium price for commodity 1 and commodity 2. Now, how to get from the previous equations here to this, I want you to do it on your own, because it's very easy already. It's just the difference now is that when you were in the first year, you use number, but now you use alphabets, in particular Greek alphabet, yeah? But they are of the same thing anyway. So this is P1, this is P2. Now from here, we still need to find Q1 and Q2 at the equilibrium, position, isn't it? How to find it? You just need to substitute all of this back into quantity function that we have here, so that you can find Q1 and Q2. Can you see the method of finding P1, P2, Q1, Q2 is just the same. It's just that, it's just the same like the way you found it for intermediate micro 1, micro 2, as well as principal. The difference is that now you're no longer using numerical examples, but you use, alphabet, because we are trying to generalize the equations that we learn in mathematics, so that it can be applied to any kind of markets rather than specific types of market. Okay, now you can try this numerical example at home, and this one is even easier than the previous example, because now it is number instead of alphabets. So try to find the solution for all of the variables in expression 26. What are the variables that you need to find in terms of solution? P1 equilibrium, P2 equilibrium, Q1 equilibrium, and Q2 equilibrium. Yeah, so all of this. You can try to use shorthand symbols, especially when you see, the coefficients. There are a lot of coefficients here. okay, to solve the problem. So I hope you try it at home. It's for your own good. Now this is just one example of exercise. You try to use to look at the exercise in the textbook and also from the internet to learn more about the use of general market equilibrium in mathematics. Okay, now what you have seen just now is that you have learned about the general market equilibrium for two commodities, but in general, in reality, we have more than two commodities, isn't it? So, what if we have a lot of number of commodities? Let's say n number of commodities. So, here the analysis is more general compared to this, isn't it? Compared to all of these. All right. So, but then we already learned the basic of a general equilibrium analysis. You just list down all the markets of commodity. You have commodity 1, you have commodity 2 here. If you have 3, you just add, the next market that is for commodity 3. If you have 4, you just list down 4 of them. But just imagine in reality, we have infinite number of commodities. So we want to put all of commodities included in the model. Then it becomes a comprehensive model because we don't leave any single, commodity, isn't it, in the analysis. Now, what happens here is that, how do we call this in the study of economics? This is what we call Walrasian type of, general equilibrium model. Have you heard this kind of model before? So when we talk about Walrasian, model, and we talk about equilibrium in Walrasian model, it has many market, it has many traders, it has many commodities. Now, this kind of model has been invented in 1951 by two very famous economists. You try to search the name of these two economists, yeah? So, these are the example of general market equilibrium, but this is on micro part, yeah? On micro part. In reality, when we talk about equilibrium in the study of economics, there are a lot of equilibrium analysis. It's not just about, market for micro. It can also be, macro analysis. It can also be for healthcare economics and other things. Anyway, let's go back to generalized, commodity case. If we have more than two, let's say n commodity, what happens here is that you just need to list down all of the market. But because it is in general, it can be rewritten as this actually. So you see here, in general, okay, we have commodity 1, 2, 3 until n. Okay, this is first commodity, second commodity, the last commodity called n commodity. Okay, so the quantity demanded equation would be, quantity demanded for I commodity that depends on price of the first commodity, the second commodity until the last commodity. That's how we read it. What about quantity supply? Quantity supply for I commodity, right? Commodity I, okay, depends on price of the first commodity, the second commodity until the last commodity. So for equilibrium condition, it's just the same. The difference between quantity demanded and quantity supply for commodity I must be 0, no excess demand. Okay, how do we know this one is talking about excess demand? Because quantity demanded comes first and then only quantity supply comes later. But if we change it, quantity supply comes first and quantity demanded comes later, what happens here? This one is actually about excess in supply. All right, now next, okay, so if we have n commodity, we can specify, this 28 as follows. Look at 29. So you have commodity 1, 2, 3, 4, 5 until n commodity, the last commodity. Then if we talk about, equilibrium conditions, then there's a mistake here. Yeah, let me erase it. Okay, so the equilibrium condition here shows that quantity demanded for commodity I that depends on price 1 to price commodity 2, price commodity 3 until price commodity n minus the quantity supply of commodity I that depends on price of commodity 1, price of commodity 2, so on and so forth until the last price of commodity must be equal to 0. That means there is no excess demand. When there is no excess demand, that means we are in the equilibrium position. Okay, so if you have 10 commodity, list down all of this. If you have 20 commodities, list down all the 20 commodities for the excess demand condition, for the quantity demand equation, quantity supply, equations, because you have 20 markers. So then, another way to write this equilibrium, because it's too long, yeah, then we can show it this way. E refers to excess, demand for commodity I, isn't it? So we know that because excess demand depends on quantity demand and also quantity supply of commodity I, and quantity demanded and quantity supply of commodity I depends on price of all of the commodities, then we can rewrite it in this form for equilibrium. Excess demand for commodity I, that depends on price of commodity 1, price of commodity 2, price of commodity 3 until price of commodity n is actually equal to 0 when it is in the equilibrium condition. Okay, so how do we solve general equation here for equilibrium? Because we have a lot of commodity and we don't have numerical number attached to this equilibrium or these equations, yeah, not only equilibrium but all of the equations in this system, then the solution is not in the numerical form. Only in the exercise of 26 that I showed you earlier, if you can remember, yeah? Yes, this one, that you can have numerical solution. But now, because we don't have number, we don't have numerical solution. We just have, the model. And when we solve it, the solution actually looks like a formula. For instance, if you look at this is the solution for price of commodity 1, isn't it, in equilibrium position. But do you see one number? No, it's just all of the, parameters. And if we know the value of C2, you know the value of gamma 0, C naught, gamma 2, then, all of the, coefficients here have some values, specific values. Then you can find the, the final solution with one number. That's why I say when it is in general form, without numerical values, then the solution itself looks like a formula in it. Okay, so here, because it looks like formula, therefore we have, even better generality or greater generality as parameters that shows general answers also, isn't it? So if we have m parameters, okay, n refers to, the total number of commodity. M refers to total number of parameters. In our previous example here, we have M equals to 12, okay? But if we have a lot of commodities, okay, we didn't know how many, let's say infinite number, we call total number of parameters as M. A1, A2, A3, until AM. So M could be the same number or different from N because it depends on, whether you have, intercept or not, okay? So here, the equilibrium prices can be rewritten as P star for commodity I equivalent, that depends on, coefficient A1, A2 until AM. For commodity I, from 1 until N commodities. So the solution here is this in general form. But we know that for sure, for each of the commodity, they have one level of price. And it has to be unique, one. Okay. Then after that, we can map the ordered M tuple of coefficients into a determinate value of each of Pi. Okay. Because if we don't have, the unique answer here, then we cannot find the exact price. Okay. Because let's say commodity A, and then it's the price is not unique for commodity A in equilibrium. Let's say the first price is £5 in equilibrium, the second price in equilibrium is suddenly, £2. Okay, then you don't have unique equilibrium price for A, isn't it? So it can't be that way because equilibrium has to be 1 point at one moment. You get what I mean here? Okay, so then we can find, if it is unique, then we can find a determinate value for each of the price. All right. So this is the example of general equilibrium. If you see the process, I did, variable elimination to solve the question. What if we have different types of simultaneous equation like this? Now let's look at the following equations. If we look at 32 is a simultaneous equations. So the first one we have x plus y equivalent to 7, and the second one we have x plus y equivalent to 10. So here we have two equations and two unknown. This is the first equation, this is the second equation. What are the unknowns? The unknowns are x and y. Is it possible for us to find any solution for x and y in these two from these two equations? Now, before we calculate and also attempt to solve the equations here to find x and y, you have to think intuitively that the first one is x plus y equals to 7. And the second one is x plus y equals to 10. X plus y here is equal to x plus y in the second one, isn't it? However, on the right hand side, 7 is not equal to 10. Now, what happens here is that x plus y equal to 7 is not consistent with x plus y equals to 10, isn't it? So when both of them are not consistent, then of course we can't find solution, although we have two equations and two unknown. Okay, so they are inconsistent. Now let's look at the second one here, 33. We have the first one here, 2x plus y equals to 12. And the second one here is 4x plus 2y equals to 24. This is the first equation, this is the second equation. Okay, so we have two unknowns, x and y. But before we proceed with the calculation, do you see any relationship between the first one and the second one here? If you look at the second one here, 4x plus 2y, 4x is twice of 2x, 2y is twice of y, and 24 is twice of 12 in it. So the value in the second one is twice as the first one, or double as the first one. So what happens here is that, because the second is just a double of the first one, so if you factorize it, it's just the same as the first one, isn't it? So these two equations are actually the same. And what happens is that both of them are functionally dependent. Okay, so when both of them are functionally dependent, then we're actually left with one equation in it. Okay, so we are left with one equation but two unknowns. Okay, two unknown x and y, but we are left with one equation because these two are actually functionally dependent. So when this happens, is it possible for us to find the solution for x and y? It's not possible. Okay, so because they are functionally dependent. The first one, they are functionally not consistent. The second one, they are functionally dependent. Now, let's look at the last one. The last one here in 34. In 34, 2x plus 3y equals to 58. This is the first one. The second one, we have y equals to 18. And the third one, we have x plus y equals to 20. Now, we have three different expressions here, but what can we do here? These three different expressions can be actually reduced to two different equations, because y equals to 18 in the second expression here can easily be substituted into the third one and also into the first one, isn't it? So if that is the case, then we are actually left with two equations and two unknown in it. Okay, so if we are left with two equations and two unknown, after that we check whether it has functionally dependent issue or non-consistency, then we can proceed with finding solutions for x and y. So it's possible to solve this equation, but we have to reduce it to two equations instead of three. All right, so here I have shown you, although we have many different types of simultaneous equations, we still need to check whether they can be reduced into, let's say, equations, whether they are inconsistent or not, yeah, so that we know whether it can be solved or not before we start our arithmetic operations. All right, now, so for this case, for instance, it's possible to find unique solution for x and y. What does it mean by unique solution for x and y? That means we have one particular answer for x, we have one particular answer for y. We don't have two particular answer for y within this system. So that's why we call it union solution. Okay, now Try to do a lot of exercises from textbook and also other sources. We need to move to the next part here. I'll guide you, but you need to read a lot in the textbook. So we are still talking about equilibrium, but this time we look at the macro analysis. So we have equilibrium in national income analysis. Let's say we have these equations. I'm sure you have seen these equations in principal macro and also intermediate macro 1 and also macroeconomics 2. So here, this is Keynesian model of national income model. Okay, so we have equilibrium income, and the condition of the rule is that whatever being produced here must be equal to whatever being spent. So this is what it is when it comes to 35. And whatever being spent comprises of consumption C, investment, and also government expenditure. And specifically, consumption is given by A plus BY, isn't it? Such that A must be positive, B must be between 0, greater than 0, and less than 1. Okay, so A in economic study is actually autonomous consumption. And what about B? B itself is marginal propensity to consume. Now, the question is, we need to find equilibrium income. We also need to find equilibrium consumption. And, these two are important, yeah? We need to find this because I and G are autonomous. All right, now, so if we need to find Y star and C star here, then you have to substitute C here back into this, and then after that, the whole thing here back into this. Then, you can see it's something like this. Y equals to A plus BY, okay, plus I naught plus G naught, isn't it? So then after that, you bring Y to this left-hand side and then solve it. Then on the left-hand side must be left with Y. The rest are the other alphabets. Okay, so I hope you try it at home. This is not difficult to do. And you can always refer to many sources to see, the solution and also the steps before you get to the final solution. But then, once you get the final solution, you need to look at the results of Y star, okay? And from the results of Y star, you need to see whether you need to put any restriction so that Y star works well, and usually Y star must be positive value so that the entire solution is defined, yeah? Okay, so and then if you try to open it to the international straight, initially we have Y equals to C plus I plus G naught, and now we introduce international trade such that we have export X naught and also import Z. Okay, then now you have to extend it because you have international trade C plus I naught plus G naught plus X naught and lastly plus V plus CY. Okay, then you put C equals to A plus BY here. You can see Y here, you can see Y here. Bring these two Y to the left and then solve it so that all here Y is on the left hand side. We call it Y star. Okay, and then the rest is on the right hand side. Okay, so again, look again. You need to see whether you need to put restriction or not so that the solution Y star here and also C star, can make sense or not. So how to do all of this? Try to look at the textbook, read the textbook. From there, you can find the answer for restriction that I told you just now. All right? So please do exercises. It's good if you can refer to other mathematical economics books such as Schaum series because it has a lot of examples for equilibrium determination and it shows you how to find equilibrium determination using, mathematics that you have learned in this chapter. So this is the end of chapter 3. Thank you very much.